Hi, and welcome back after the break. It's week 6, and Charles, we're going to be doing some stuff now. I think I'm getting at this right. You're going to discuss some stuff this week related to getting a larger exposure. Well, actually, there's two things here. For my world, there's a whole thing about I want more latitude on my camera.
Okay.
And so in film, I used to get that, and I used to sit in a telecine suite and actually cut my teeth on making telecines and helping design them. And in that sense, we had a lot of latitude. We would just pick which bit of the picture we would then transfer to, say, HD. Of course, what people want sometimes now, so I want my highlights and eat them too. So you say, okay, well then you're kind of tone mapping. You're trying to take more latitude and cram it into...
Right.
And that's got a problem in terms of mapping because, you know, you can get the mid-tones effectively to become quite unpleasant as you start packing stuff in.
Right.
And also, some people do it by doing regionalised stuff. Then you start getting these halations,
yes,
and it's kind of ugly.
Yes.
So that's some of what you're talking about, but not all of what you're talking about today.
I will talk about some of that, and it's the classic HD scenario where you take this basic curve in the midtones and then crunch or extend the knee to affect the highlight treatment. And that's an aesthetic thing. It could be implemented by the cameraman, changing the camera controls. It could be done in post. That's part of it, and that does address the latitude of a particular scene. But there's also an overall generic mapping that you need to do to go from a very bright environment like outdoors to a very dark environment like a cinema and make it look like it's outdoors. So there's a requirement to increase the contrast of the image a bit and increase the colorfulness. That also you can call tone mapping.
Okay, let's check it out.
For this class, I'd like to address the deep principle, what I consider to be the deep principle of tone mapping in HD and digital cinema. And I've alluded to this in a few classes already, but now I'd like to first give you the deep fundamentals and then describe how we do this mapping. And you'll discover by the end of this class that the deep principle is intimately connected with the Academy workflow. In particular, it has everything to do with the reference rendering transform, the RRT of the Academy workflow. So we start by having as our conceptual foundation the movie Van Helsing, whose cinematographer was Alan Davio, and he figures in the story, as you'll discover later on. So consider acquisition and post or DI and exhibition or presentation of a movie. We'll start with a scene and some talent. And obviously, in order to capture and record this, we'll need a camera. We need some sort of recording or processing machinery, and we need a display. And we'll have a human observer looking at that display. And in principle, as our first guess toward how to build a system, that accomplishes this task, we'll consider that the viewer of the scene as presented from the display should, in theory, be able to compare what he or she is viewing with the original scene. Well, generally not literally the original scene, but the viewer should be able to map the display into what the original scene would have looked like. So there's a line on the drawing that I'll add, which is this comparison line, where the viewer hopes that those two visual stimuli are comparable. Now, I think if you look at my 1996 book, Technical Introduction to Digital Video, I think you'll find this illustration. And the news that I have to report to you today is that this illustration is basically wrong. And it's wrong on 2 counts, which we'll discuss over the next 10 minutes. But let's march forward, because this is a reasonable starting point. And it's conceptually important to discover why it doesn't work in detail, but that's a discovery we make in a little while. Now, consider this diagram to take place at production. So consider this person to be looking at the display at the completion of poster DI. And when that imagery is approved and mastered and distributed, there's another channel, a distribution channel, and an ultimate consumer viewer, whether that viewer is in a cinema, if we're making a movie, or whether that viewer is a consumer in a living room, if we're making a TV show. That's not so important for the principle. So, but before we get there, one highly significant thing happened during the last 8 or 9 years that we should pay attention to, and you'll have to look at the drawing really carefully as I change slides to see what changed. That's what changed. All of a sudden we went from CRTs to flat panel displays, typically LCDs. And the main significance of that is that in the era of the CRT, gamma, or to use the really technical term, the electro-optical conversion function, the EOCF, just loosely speaking, gamma of the display, in the CRT era was fixed by the properties of the cathode ray tube itself. And when it was the mechanical and electrostatic properties of the CRT that determined gamma, gamma wasn't adjustable, and all CRTs had approximately the same gamma because they had approximately the same construction. All bets are off on flat panel displays, or if you want to call them fixed pixel displays, because they don't share the physics of a CRT. And so now we need to standardize that electro-optical conversion function, and that's the importance of BT1886 that I mentioned last class. Standard for HD display, a power function of 2.4. So now back to the main storyline. We're going to take that image and distribute it to the end consumer. So here's our consumer display, and I'll prove that I'm kind of a groovy, up-to-date guy by drawing the distribution system as a cloud. We don't particularly care how the distribution takes place. We assume that we push the bits out through the distribution channel, and the bits simply get delivered unchanged, whatever path they happen to take through the distribution system. So now we can think of a consumer, either in the cinema or in the living room, as viewing this image. And our conceptual model for faithful image display is that in principle the consumer ought to be able to look at the original image at the completion of post or DI, and those two should compare equal. That's the goal of faithful reproduction. I don't particularly like the word reproduction because literally it should mean production again, and of course we don't produce again. So I'd prefer to talk about presentation. But we want to present something very comparable to the image that the creative team experienced at the completion of poster DI. Now, if you think about this a little further, you realize that a cinematographer like Alan Davio, in making Van Helsing, to pick just one example, isn't probably attempting to recreate for the viewer exactly what was in front of the camera. The cinematographer is trying to tell a story through visual means. And you can do anything you want in production, in post-production, in post and DI. Anything is fair game as long as it meets the goal of delivering the visual story to the user. And from that point of view, you think to yourself, what's in front of the camera, and mapping that into the post and DI process is really just the means to an end. Now, let me give you a very real example of a case where there's a dramatic difference between what was in front of the camera and what is the finished product at the end of post and DI. And my example is the movie Pleasantville. And I don't have copyright clearance for Pleasantville images, much as I tried, but I did recreate this image in the visual style of Pleasantville, where the protagonist of the story is portrayed in color because a certain thing has happened in the story that has given color to that person, and the remaining people in the scene are portrayed in black and white because this event hasn't happened to them. So the story involves people in color and people in black and white in the final product, but that's not what they looked like in front of the camera. The movie is absolutely not portraying accurately what was in front of the camera. Instead, tools in post and DI have been used to change the visual content in order to tell the story. So from that point of view, now we go back to our big block diagram and we say, what's in front of the camera is only a means to an end. And in certain movies, we can think of the post and DI process as making dramatic manipulations, and the goal of matching the scene to the final product in the studio is not important. What is important is faithful portrayal of what was seen at the end of production. So now we can go one step further on our block diagram and say the post and DI process can really be a black box, and we'll turn it black. And faithful portrayal is delivered when the mapping to light to the viewer is comparable. And here I'm including a photo of Alan Davio, and he's smiling because I think he's happy that this situation will be the situation that he wants. Actually, he's smiling here because he's just won an award. But I did have a conversation with him about this principle, and he did express agreement in principle that this is a good way to look at the problem. Now, this model of faithfully mimicking in the exhibition scenario the electrical-optical conversion function at mastering, that was missed in the HD community for a small number of decades. So we have the historical HD standard, 709, you're all familiar with, that starts out looking like this. This is just the top half of page 1. And 709 only standardizes the optoelectronic function, that is to say the function in the camera, which, according to my argument, is not important. Well, it's important for engineering purposes, but it's not necessarily important for creative purposes. What 709 neglects to do is standardize the mapping to the studio reference display, which should then be the prototype for consumer displays. And luckily, that gap was filled in March of 2011 by the new standard BT 1886, which calls for a 2.4 function. But it doesn't say what viewing environment is involved with looking at that image, and it doesn't say the reference white level in terms of absolute luminance that the viewer will experience. There is common industry practice for those other parameters, and roughly speaking, HD mastering is done with the display set for a reference white of 100 nits, an ambient illuminance in the room, and I'm picturing that as falling from the ceiling, of about 1 lux, which is dramatically dark. Most of us have been in HD mastering studios and we've experienced that. And a surround condition, what's the luminance level surrounding the image? And that's, in today's practice, around 1 candela per meter squared in the surround. Now, those parameters haven't been standardized yet. I hope they will be at some point. But the 2.4 function on the way out is built on that sort of environment. Now, we can ask ourselves, how does the appearance of the image change if those parameters change? For example, if diffuse white in the scene, like a white shirt, is portrayed at 24 nits instead of 100, and by the way, that would be approximately the case in a typical movie, and the surround is completely pitch black instead of 1 nit, how does the appearance change? And the answer is basically that the colorfulness and the contrast visually both drop. Well, we'll have to fix that, and in a moment we'll explore what we do to fix that. On the other hand, we may be going out into an environment where it's a bright display, perhaps 320 nits instead of 100, where the ambient condition is quite bright. The surround might be 20% of reference white luminance instead of 1% of reference white luminance. The appearance will differ. In practice, we overcome these changes in the viewing environment. So think of 3 of them. Think of cinema, where even though peak white can be as high as 48 nits, typically we leave a lot of room for specular highlights, perhaps as much as 1 stop. So even though peak white is 48 nits, a portrayal of diffuse white may only be 24, and it's pitch black. HD, where reference white is 100, diffuse white is probably close to 100, and the surround is about 1% of 100 nits, to a bright environment such as you might find in desktop PC computer graphics. Roughly speaking, the way we can adapt the image data to these different environments is by changing the gamma. HD, I've explained, has got a gamma 2.4. To go to a really dark environment like the cinema, to achieve the correct image appearance, you'll want to increase the gamma a bit to about 2.6. Well, DCI, or SMPTE 431-2 standard, the standard for cinema presentation of digital material is gamma 2.6. It's not 2.4 because it's way darker. On the other hand, to go to a really bright condition, you'll want to take that image data and go out through a gamma of about 2.2 to 320 nits in a really bright environment. That's the standard sRGB for computer graphics, commodity computer graphics. And those gamma differences basically at the viewing end adapt the material to different conditions. Now, where you live in a VFX shop, you're probably running sRGB monitors, but not at 320 nits. You may have backed them off to 100 nits, looking more like an HD mastering situation. But you might not have a room that's as dark as 1 lux or a surround that's as dark as 1 candela per meter squared. So you may want to have gamma not quite as high as 2.4, but not quite as low as 2.2. You may choose gamma 2.3, for example. And those issues are best dealt with using monitor calibration and monitor alignment software. Now, it may be going overboard, but to drive the point home, think about what it means to say that I've got an HD Cam SR tape and it's got 709 material on it. What that means is not that I captured it with factory settings on the camera. That's what reading 709, the standard itself, would have you believe. But what it really means in practice is I'd like you to display this out through your usual HD display path. And in terms of the story, I might have shot a ghost story where the protagonist uses infrared night vision goggles which show the image reversed. And I might have got material here which is black for white, inverted. But if that's artistically the goal of the piece, when I say this is 709 tape, what it means is display it out through an HD display. It doesn't mean I use that curve that's in the 709 spec. So that's the importance of the standard EOCF. That's the electro-optic conversion at the back end. So where the standard suggests that a 709 tape involves this curve, that's not actually true in practice at all. It may involve curves that are adjusted by the cinematographer, the DOP, all over the place or even inverted. What I really mean when I hand you a 709 material is I'd like you to go out to the display through a curve like this. And this is the BT 1886 standard, and it says just 2.4 gamma. And this argument doesn't just apply to data laid down on HD tape. This could be 709 data on a Codex disc pack or any other kind of material, any other kind of recording media that you want. When you're capturing digital imagery for HD, for digital cinema, at one level you'd think you can do the science to capture the luminance levels on a certain scale. The cinematographer will set exposure to put diffuse white or put 18% gray at the desired spot. You might think that neglecting gamma correction and log coding and all those other technical issues, you might think that your goal would be to move those luminance levels from the scene in linear light space into linear light values in the display space. But of course, the absolute luminance levels are dramatically different. In the case of the scene where I find myself today, the illuminance is around 100,000 lux. The luminance reflected from a diffuse card is perhaps 30,000 or perhaps as little as 10,000 candelas per meter squared. But when displayed at HD, a diffuse white or even maximum white will be 100 candelas per meter squared. That huge shift in absolute luminance levels is associated with a shift in the visual perception. Colors look less colorful when the overall illumination is lower. And the problem of using a shot like this, captured out in the daylight, and just directly presenting it in post, is that the colors look less colorful. And reproduced correctly, mathematically, this scene would look like twilight if displayed at 100 nits. It's an extremely important aspect of post or digital intermediate or grading that a visual compensation of that loss in colorfulness takes place. And the technical term for that process is picture rendering. In some cases, that picture rendering mathematics is built into your color calibration system. But of course, the colorist in post or DI gets to increase or decrease the colorfulness to achieve the look of the image that the colorist, the DP, the producer, the director think is appropriate for that scene. Now, if you achieve the look that you want to achieve with the picture, nothing else really matters. But we would like to have a solid basis of science upon which to build that look. We'd like to have a visually appropriate starting point. And most of the grading systems have got transformations built in that give you that starting point. Then the colorist works from there to achieve the look that he or she wants to achieve. I mentioned a few minutes ago that shooting at very high luminance levels like outdoors, you have to pay attention to where diffuse white sits on the exposure scale from black to the maximum available from your imaging system, from your sensor, from your camera. So here we're outdoors on a very bright, clear day in North Sydney. The illuminance from the sun is probably 100,000 lux, and that illuminance translates to luminance by a factor 1 over pi when you express these quantities in the standard units. So 100,000 lux falling on this nearly perfect diffuse reflector is presenting luminance to the camera of about 30,000 nits. Now that represents the top end of diffuse reflectance, but there's elements in the scene that are dramatically above that in the case where the scene contains elements that have mirror-like or specular reflections. And we've picked this white car in the parking lot to show you that it's got diffuse reflectance roughly comparable to the reflectance of our piece of paper, but it has specular elements as well, this glint from the sun reflecting off the back window, and some glints from chrome and shiny parts on the car. So we'd like to set our exposure so that diffuse reflectance is comfortably at the top end of the scale, but we've got lots of room above that to handle these speculars without clipping them. And at the other end of the scale, we've got elements in the scene which are quite dark, like underneath the car. Ideally, we'll have an exposure setting that captures that in case there's elements that are important in the story in dark portions of the picture. So the challenge is, how do you capture and record very dark elements, very light elements up to diffuse white, and even elements above diffuse white? It's the cinematographer's job to pick exposure to handle the range necessary for a particular scene. Now, when those exposure levels are captured, of course, they're turned into digital numbers by the camera. In order to do VFX on those shots, we'd like to be able to translate those camera numbers back to the scene values comparable to what were the light levels in the actual scene. That's where the VFX will be built. At some point, though, in the production process, we're going to want to manipulate those numbers to bring them into the range that's suitable for display, either HD, where reference white is 100 nits, or digital cinema, where reference white is 48 nits. But that 48 nits, that's the maximum value of luminance for digital cinema. And ordinarily in digital cinema, we'll pick a presentation value where diffuse white will be somewhat lower than 48, maybe even one stop below 48 nits. In other words, diffuse white at 24 nits, halfway up the linear light scale, in order to leave room for those specular, shiny things, and in order that highlights not blow out. Now, I talked about the curve that's used in practice in an HD camera, and there's a lot of knobs, 8 or 10 or 12 of them. And you may, if you want to just immediately capture material ready for HD display, you might want to wing those knobs on set. But doing so doesn't, in a traditional HD camera, record any metadata. It just records the image the way you want it to look. And if you want to do VFX with that imagery, well, you're almost sunk, because VFX really needs to be referenced to the light values in the scene and not the light values intended to be displayed. So for that reason, for a VFX-friendly capture, you want to know exactly what the curve is. And that's a good reason to lock it down. And the log codings that are standardized ideally will be standardized with an equation that you can hand to the VFX shop and say, here's how you undo my image data to go back to linear light. That will make the VFX job very easy. Now, historically, HD cameras had all those knobs because it was the goal to put more or less the finished program in the can. You could always go and tweak it later, but the idea is this mapping into display space happens at the camera. And the entire scene referred model says, push that back, don't do that. Use a curve at the camera to maximize the visual performance of recording, but lock down what that curve is, take away the knobs. So historically, the knobs have got a really horrible user interface. Literally, these shots were taken mimicking the user interface of a Sony f900 camera. Things are getting better now, but historically, the DOP or the videographer would have dialed in, say, for this example, 0.45 gamma, which I've already explained to you is not actually effectively a 0.45 power function. It ends up being a 0.5 power function. So it was very difficult to map back from an HD shoot into anything that's VFX friendly, and this is what the Scene Linear framework is trying to repair. So these menus are very obscure. Now, Panalog was one of the first. I guess Viper FilmStream was the first logarithmic-based mapping that was locked down in the camera that produces data that's easily inverted at VFX to get back to linear light, but still recordable in a 10-bit HD recording path. Now, Panavision, as far as I know, never did release the formula that establishes this curve, but they did release a spreadsheet with 1,024 entries, and you could numerically invert that spreadsheet, and Panavision probably provided the spreadsheet in both directions, from Panavision code to linear light and from linear light to Panavision code. So that's a good step, but I'm much happier with the log coding curves where the manufacturer simply provides you the formula, so you can analytically invert it. And there are some codings that people have used to shoot movies where the formula or the mapping or the lookup table or the spreadsheet is not available. I'm thinking in particular of Sony HyperGamma, which is living in a space kind of halfway between the traditional HD model where you do all of the rendering in the camera and the linear light model where you capture a wider range of scene image values than is typical. In the case of HyperGamma, Sony apparently considers that mapping to be secret sauce and have not released the mapping. So if a movie maker decides to use HyperGamma in capturing a movie, it's a big problem for the VFX shop, because the VFX shop can't immediately and easily map back from HyperGamma coding into linear light coding. And I know of at least one VFX shop, and there's probably 5 or 6, that have been forced to go and rent a camera, set it up like the movie DOP set it up. There's 4 different HyperGamma settings. You have to figure out which one was used. Shoot a test card, do a frame grab, take the measurements, interpolate, try to estimate what the curve was, and use that to undo the mapping of the data. And you can imagine this is a big mess. So having a curve provided as a formula is a big win. For this class, I've been telling you about the overall pipeline from acquisition to display. I've explained a little bit about mappings out to the display and how gamma might have to change depending upon display conditions and viewing conditions. I've explained how the historical 709 standard really just talks about the camera mapping, which is not the important part. Now we've got a really good standard for HD at the back end, BT 1886, that says 2.4 gamma. We've already got a really good mapping at the back end for cinema, standardizing gamma 2.6. And I've talked about the concept behind historical HD acquisition, do all the picture manipulation up front to produce data that's immediately ready for a display. And I've talked about the new model for cinema acquisition, just acquire the light values, map them into a good perceptually uniform space, but have a mapping that's perfectly invertible. What we're missing, and what we'll talk about in our next class, is the mapping that has to take place in the guts of the post or DI domain that goes from potentially very high levels of illumination in the scene, perhaps 10,000 or 30,000 nits, to a rather low level at presentation, 100 nits for HD or 24 nit diffuse white for cinema. There's an important mapping there, and there's a historical way that that mapping has been done in HD, and that's basically manipulating the curves in the camera with reference to the 2.4 curve at the back end. And there's a new way to do this that's been in development for the last 3 years or so at the Academy. It's just getting pretty close to being released as the Academy Image Interchange Framework, and the mapping part of that framework is the reference rendering transform, where we're headed for the last few classes. We'll talk about that big transform in the middle in our next class.
Okay, so that's fascinating to me, and I'll tell you why. Because as a compositor, and I actually said this a little while ago when I was talking to John in a DoD like about a month ago, because we discussed this. As a compositor, I always say, if you're going to shoot somebody for compositing them into an exterior scene, go outside and shoot them outside.
Right.
Now, I said that because I said it's really hard here. If we were talking, I would have said, and you weren't you, you're a director. I said it's really hard to do it here because you're never going to get parallel light properly.
Right.
Plus, because of inverse square law, this light is much closer to my head than my feet.
Right.
And so consequently, there's a big drop-off on my body. Doesn't happen with the sun.
Right.
I could have come up with 10 reasons why the light quality on me here from internal lights in the studio was going to make it hard to match the external. What I wouldn't have said is that we're in a lower light situation in here, and outside we're in a high light situation, higher light level situation, and consequently we have saturation and just sort of scaling issues. So not only was I probably right with that stuff about parallel light and stuff, but literally that process of shooting the same thing, like let's say we had a scrim up, so we're not talking now about whether or not I got direct contrast rate.
Diffuse light.
Yeah, but I put it, exactly. I put a diffuse light, big diffuser outside, but still it's bright sunshine hitting it, much higher light level. Come in here, have diffused light. We're still going to have this sort of inherent difference that maybe I can pick as not selling the composite properly.
Well, it's a visual thing.
Yeah.
That when light level reduces, our notion of colorfulness reduces, even though the Macbeth chart chips hit exactly the same spot.
This is where it's fascinating to me, because I could actually, in a flame suite, go and sample those and say, hang on, have we got the right chrominance here on a vector scope?
Right.
And it's going to be, it's like, yes, that's red.
Well, and there are ways to fix those things in a compositor in post, of course. I mean, you've got a chroma dial. And at the end of the day, in all of these production techniques, the picture on the surface of the mastering or approval display, that rules. Yeah. So anything you do to get the correct picture up is fair game.
No, totally.
But I will say that the picture you end up with will have a colorfulness that gives the characters an appropriate feel that makes you think that they're indoors in a dim evening situation or outdoors in the bright
Because that's what we're
sunshine.
looking for. We're looking for little clues that your brain takes as to this picture
Right.
isn't right. Sometimes that's light wrap, but what you're saying is really interesting because I could, as I say, given 10 reasons why it was better to do that outside. Now I have an 11th, maybe a 12th. No, but it's great because
Right.
I just absolutely did not know that. I've been compositing for like 20 years.
And your eyes rule in the end, so
Yeah.
you have to satisfy
Yeah,
vision.
we would adjust it to make it look right.
Of course.
But of course, from my point of view, it's great to know what's going on because, you know, it's one of those things that you can adjust for once you're conscious that that's a property
Right.
that you need to be adjusting for.
Well, I'm delighted to be able to give you that little piece that fits
I'm
into your...
so glad I enrolled in this course. Oh, wait, I didn't. Okay. Keep the questions coming in the forums. Thanks so much, Charles.
Good.